All right, everybody, welcome back. In this video, we are going to talk about information from section 8.11 from AP Calculus, volume with the Washer method, revolving around the X or Y axis. Okay, so we've already learned how to find volume using the disk method, and the Washer method is very similar to the disk method in its core. The big difference between these two is when they're used, and there's a little bit of difference in how we set them up, but basically when we talked about the disk method, we said we're going to use that anytime that the region has the axis of revolution as its boundary. Well, the Washer method we're going to use anytime the region does not have the axis of revolution as its boundary. Okay, let's start by looking at a region that will lead to a washer-based solid. If I take the region pictured in this graph here between y equals f of x and y equals g of x, this will lead to a washer-based solid because there's my region and here's my axis of rotation. And so this axis is not a boundary of this region, therefore it's going to be appropriate for us to use the Washer method. And the reason why the Washer method is useful here instead of the disk method is because of this gap between the region and the axis of rotation. That's what causes this to be a washer instead of being a disk. Okay? Now, if you think about spinning this solid around the x-axis here, if you think about what happens, we've got this, outer boundary that's going to form the outer, what I call the outer radius of the washer. Okay, so if you see that, if this curve y equals g of x didn't exist and we were just finding the region, all the way to the axis, this would be the radius of a disk. And so when we spin this around, it forms a disk-shaped solid. But because of this inner radius, it also forms a disk-shaped hole inside of that disk-shaped solid. And so when we make this new three-dimensional solid, this washer-based solid, what happens is, in essence, we have a disk-based solid with a smaller disk-based solid hollowed out of the middle. Okay, now if you try to imagine a slice of this solid, here's what they'd look like if I took a slice of this solid and cut it out. F of x, which was my red here, forms the radius of the outer cylinder. When I'm looking at it from side view, I can't really tell, but here from front view, it's the radius from here to the outside. It's the radius of that big washer, or of that big disc. And then here with the turquoise, that was my inner radius, which is, this radius right here that forms the inner circle. And when I use those, what happens is I form a disk with the outer radius, the red one, and then there's a disk that gets hollowed out of the middle. And so in essence, what we've got is we've got the volume of this disk minus the volume of this disk that makes the volume of our washer. And we explain that down here. The volume of the outer cylinder here is pi r squared h. So if we put the radius in there, it's represented by pi times f of x, quantity f of x squared dx. The inner cylinder here that gets cut out is again pi r squared h. In this case, the radius is different. G of x is the radius instead. So that's the volume of the cylinder that gets cut out. So if we subtract the smaller cylinder from the bigger cylinder, we get this expression right here, representing the volume of this particular washer right here. If we factor out the pi and the dx And unfortunately it got split over 2 lines, so I'm going to just rewrite it here. If we factor the pi out in front of this and the dx out behind it, we end up with our integral expression, and in our integral expression we just have the outer radius squared minus the inner radius squared. And that's what's going to form our integral setup. Okay, on to a little bit more information. So if we take the integral from one end to the other, we take the integral from a to b of this, that gives us the volume of the given solid. Just like when we were talking about disks, remember, it's important to note which axis we're revolving around. If we're going around the x-axis, we want everything in our integral to be in terms of x, and our limits of integration are going to be x-coordinates, starting with the lower limit of integration being the left endpoint of the region, and the upper limit of integration being the right endpoint of the region. And when we go around the y-axis, we want everything to be in terms of y. And we want the y-coordinate of the lower endpoint as our lower limit of integration, and the y-coordinate of the upper endpoint as our upper limit of integration. All right, so there's my setup for these problems. So let's go ahead and do a few examples here. One other thing you should note is that the function f here represents the boundary that is farthest away from the axis of revolution, and the function g represents the boundary that is closest to the axis of revolution. So let's go ahead and we'll do some examples here. Example 1. We're going to find the volume of the solid generated by revolving the region bounded by y equals x squared plus 4 and y equals negative 1/2 x plus 5 around the x-axis. So first, think about what this looks like. I've got y equals x squared plus 4. I've got y equals negative 1/2 x plus 5. And so this is my region. All right. So to set this up, I'm going to take pi times the integral from one end of here to the other. So I need these limits of integration. I could go ahead and solve this system of equations by hand, but most likely if I'm doing this problem, I'm going to have access to a calculator because most of these volume of solid questions show up on calculator section of your exam. If they don't show up on the calculator, if they show up on the non-calculator, you're dealing usually with easier, some of the easier curves. This is one that I certainly could do by hand, but it's a little uglier than you would expect on a non-calculator section. So find my intersection of these 2 points. And my x-coordinate of this is going to be my lower limit of integration, negative 1.2807776. And my upper limit of integration is going to be the other intersection point. Go ahead and find that. And that's going to be 0.780776. And then all I need is my integrand. Okay, so looking at this region, this line right here forms the outer boundary, and so the outer radius is going to be from that boundary down to the axis of rotation, in this case the x-axis, and so the distance between those two things is just the function. So that outer radius is going to be negative 1/2 x plus 5, and the inner radius is going to be based off of the parabola, and so that's going to be x squared plus 4. And we're going to integrate all of that with respect to x. So I break out my handy dandy calculator, and I've got everything set up right. So I've got pi times the integral of quantity negative 1/2 x plus 5 quantity squared minus quantity x squared plus 4 quantity squared with respect to x from negative 1.280776 to 0.780776, and this should give us our volume 43.123. That's a cool answer, 43.123. Something you want to notice here, common student error that I've seen over the years, notice that we've got one quantity squared and another quantity squared. Because this is the outer radius squared and the inner radius squared, a common student error I've seen over the years has been to take the difference of these two functions and then square the result. That's something you want to avoid doing. That's something we see, a lot of times when we're doing cross-sectional solids. But when we're doing solids of revolution, we really don't see that happening too much unless we're, revolving around a line. We don't really see two different things inside of parentheses being raised to a power. So we've got to have two pods here in our integral, one for each radius that forms the washer, the outer radius and the inner radius. All right, we're going to call it quits for this video here. We're going to come back and do a second video with a couple more examples of finding volume using the Washer method and going around the x-axis and y-axis. So join us then. Have a great rest of your day. We'll see you next time. Bye-bye, everybody.